Okay, sorry about that, folks. I was just checking the audio and I just realised that there was a setting that had changed. So I do apologise for that in advance. Um, that's a little bit of an error on my part, so I do apologise. Okay, sorry about that, folks. Yeah, everything's just checking the audio now, so and yeah, I do apologise for that. So it seems like everything's okay again now. One of my audio channels got turned off, so that's a bit annoying. Yeah, okay, it works now. Thank you, Canbin. Alright, so yeah, it's just that little hiccup. So a couple of minutes in, but there you go. It's all good now. So welcome. Thank you very much, everybody. Alright, so we're awesome. We're off and running again. So we're looking at some new ideas now. Beyond high school, we're thinking about Amana, just give me a thumbs up that you can hear me now, because I've just noticed you've made a bit of an effort with your message. Amana, just give me a thumbs up that you're okay with the, or give me a yes now. That'd be great. So what happens is that we have some values that go beyond our high school ideas, and so we need to start to develop those from this week in. Remembering that we're sticking to the basic and fundamental strategy that we've got to get both linear algebra and statistics done, and then we can have a lot of fun with our mathematics. That's the point. So a bit of hard work in the beginning, and it'll come back to us later on. Alright, so random variables are something that we'll look at today, and the nature of random variables. We'll have a look at some functions today as they relate to variables. What is a variable? Well, a variable is something that we've introduced previously, and ostensibly it's talked mainly about those parameters from a population. If we take a reflection of those in statistics, the statistics sample, the sample's random, of course we want that. Okay, thank you, Amana, I appreciate that. So from the sample, we'll expect to have randomization, but the variables could be the mean, they could be the standard deviation, they could be the variance, they could be any one of those things. So we've kind of graduated from just thinking about measures of central tendency and measures of variance to now thinking about variables. Variables are the things that statisticians are interested in. So an experiment is a process of obtaining an outcome when an outcome is uncertain. So again, the language is the same. It's uncertain how things are happening, and so we deal with uncertainty and probability. It's a normal world when we deal with uncertainty. It might feel like it's a bit uncertain at the moment out there, but for statisticians, they're quite comfortable because they have a sense of what that actually means. It doesn't mean doom and gloom. It doesn't mean the world's going to end. It doesn't mean it's a tragic place to live. All of those things are not true. It's still a wonderful world. It's a wonderful life, and we've just taken in our stride the various difficulties that are coming along, and we've got statistics to help us realise the reality. So a random variable is a numerical variable whose value can change from one replicate of an experiment. So if we repeat the experiment, the random variable's value will change. So as we go from one experiment to another, replicating, repeating, replicating, repeating, replicating, repeating, the random variable changes, and so we expect that. And so what we see, sample means and sample means and standard deviations are examples of random variables, okay? And they are very different from sample to sample. You can't make me laugh while I'm working, please. It's not fair, okay? So population means standard deviations are not random, okay, because they're populations, and that's a central tenet of statistics. If you like, populations are basically unobtainable. All right, so for a couple of examples, let's think about those. If we have experiment one, very simple ideas, bit of a soft start today still. Pick a student at random from the class, so that's not picking boys or girls, it's not picking tall or short, it's just randomly coming up with someone purely by accident, if you like, and then we can assign a variable. Okay, so we're not picking by height, we're just picking, and then x becomes, for example, the height, all right, of the student. Throwing a die, you've seen that lots of times now through school, and so what we've got is a possible outcome of the die. Okay, every time we take a new pick of a student, we'll get a different value of height. Every time we throw a die, if it's a fair die, then what we'll get is we'll get a different value every time you take a new sample. So that's a property as much as it is a phenomenon of what's going on with our experiments. Okay, so random variables can be continuous or discrete, and they're remembering that we said random variables were continuous in nature. So they can take on measuring values. So when we think about continuous, I think I said this last time, measuring values, okay, and electrical current, length, pressure, temperature. It doesn't matter if you're experienced with those, only that they are things that can be measured, as opposed to things which can be counted. So the counting numbers in the set of numbers is applied to a discrete random variable. So we've got two types: continuous random variables, continuous RVs, and discrete RVs. Okay. Well, you should have, because it's on UTS Online. I just saw it before when I was looking for. I really don't want to interrupt the lecture for this, but because I'm such a lovely man and I love looking after you guys so much, okay, I'm going to just do that. So you got to go here. You guys should have had all that. And I think I even saw my colleague Talib, he was on this, your one, isn't he? So yours won't be quite like this, because I'm pausing now to help you out. Mathematical Modelling 2, so you click on there, and there's your announcements for the day. And guess what? What was your question? Where do we get the meeting ID for computer lab classes? Why don't you go to the tutorial class and ask there? That would be a good place to start. Okay, why don't you ask your tutor? That would be a good place to go. Okay. Yes. Go to... Well, hang on a minute. Actually, I can do better than that. I can do better than that. No, stop trying to be funny. No. I'm getting very, very distracted now. So I can show you now, Mr. Lieutenant, if you're prepared to let me do something, I will show you this. Just pause for a minute. We've got a few tools available to us as staff, so I'm not showing you how I'm getting this. Or actually, I don't know your name, so that's going to be a problem. This might not work. So, yes, Mr. Lieutenant, if you want me to make this work, you're going to have to, ask your tutor, and then go on to WebAssign, and you look up your My Timetable. I was going to look up my timetable for you, but I think I'm wasting time, so I better stop. Wasting time. Look, if you're really stuck for that kind of info, go to My Timetable. You'll have a computer lab, and it'll have an activity number 1. Okay, and then when you get the activity and you go on to WebAssign, because I think all your labs are online, aren't they? So you go to WebAssign, you log in. Yours will be yours, not mine. Okay, and then what you'll do is you'll go to the student view. You're already in student view. I'll pick your subject because I've got my other subject there. And then if there's a and the other thing you need to do is check your timetable. So at the moment there aren't any, but if you go to My Timetable, you can't log on to this one, so that's not much help. But if we did 33.230 in the spring, and I'll do that, computer labs, then they're all your computer labs. So there's some 9, 3 o'clock, there's 1, 11. So that number on your timetable matches this activity code, this column here. Okay, so whatever you've been allocated to, it goes there. Okay, so if someone was willing to give me their student number and they didn't mind everyone seeing their timetable, I could quickly call that up and show you that that activity code there is the one that gets allocated. Okay, so we might leave that for another time. Okay, alright, that's enough of that. Let's get away from this and all of that. Liam, are you sure about this? Okay, I'm not doing what I'm supposed to be doing, but I know it's the beginning of the semester and I know you guys are keen to understand how all this stuff works. So the question that you asked me, that I was asked by previously, was, okay, so if I go into student and I type that number, now that I have your permission to do so. Okay, there you go, Liam, that's you. If I double click on this now, if I single click on this, it gives me your timetable. But what I can do, and you probably didn't know that we could do this, is I can double click on it and it brings me up and it says Jason on behalf of Liam. Now I can't allocate, it's a read-only thing. But if we go to mathematical modeling in the spring and we look at the computer, okay, you have been allocated in Liam's example, and thank you so much, Liam, for doing this. Props to you. You've been allocated activity 19. Okay, so activity 19, Wednesday at 10. So that's Liam's lab. So you guys have got to look that up in order to know when to go to WebAssign. And when you go into WebAssign, there'll be a test there for you, and then you'll be able to join the dots, I would have hoped. If you're stuck beyond that, send an email to your subject coordinator. Okay, alright, that's enough from me at the moment. Let's just pause on that. Thank you, Liam, for that permission. I appreciate it, but let's get on with this, please. This has been interesting, but it's consumed 5 minutes. Alright, so you get your labs, okay? You get your labs from your My Timetable. So I hope that was clear as mud. Now let's get back to a random variable, okay? And thanks, Liam, thanks for that. Okay, so discretes and continuous. For example, what do we call the experiment 1, the height, which is it discrete or continuous? We want to classify that. Let's put away the private talk, please, and let's just stick to the lecture. It's all recorded, remember. You have been warned about UTS policy, please. So someone like to tell me what the classification for experiment 1 height is, please. Is it continuous or discrete? Continuous or discrete? Yes, it's continuous because it's something that we would measure. Okay, the roll of the dice. It's alright, mate, no worries. I'm glad you're doing the right thing. We're all doing the right thing. Yes, that one's discrete. Okay, so we've got that basic classification happening, so that's good. Alright, the next thing is quickly having a look at classifying each of these. What I'd like you to do is, if you've printed yours out, just go and put a C or a D next to each of these. Okay, so the lifetime of a biomedical device after implant in a patient, so that's about time, that's a measurement. So I'll do them slowly, but you can run down and do them. So the number of times, so that's a count. So that's a count, so that one is discrete. The strength of a concrete specimen. So the strength of a concrete specimen is something that you can measure. Okay, there's two forms of measurement. There's a destruction test, where you get a beam and break it. Okay, and the meter changes. And the other one is a slurry test, where you get a shovel and you throw it down and it makes a pile, and depending on the nature and height on site, you can decide if it's going to meet the MPA requirements. and that's a slurry test. That's a real thing. It's not a story. Okay, so that's a measuring thing. So we can measure that. So we might say that they are continuous. The number of luxury options selected by a buyer. Why would they put options on a car? Just to make you spend all your money. So we can count those options. The proportion of defective solder joints. So we've got solder joints on a board, so we would count those. So that would be a count. Okay, so we would call that discrete. The weight of an injection molded plastic part. Okay, so that's a weight, that's a measurement. So that's continuous. Okay, and then for this one, the number of particles in a sample of gas. So we'd be counting those. So counting particles. So that would be D. All right. Alright, so in that regard, fairly straightforward, isn't it, what we're asking you to do. Now this is where it's going to start to get a bit interesting, so I want you to pay attention to the detail, please, because it makes a difference, particularly when you do any kind of computer work. So a random variable is said to be discrete if it can be equal to a finite or countably infinite number of distinct values. Now what we've got here is some nomenclature that I want you to pay attention to. I'm not concerned about the text, the context. I'm not concerned that it's transmitted through a digital transmission channel, received in error. Let x, the random variable, be the number of bits in the next 4 bits transmitted in error. So x is the number of bits transmitted in error. Based on past data, we can determine that the probabilities now, so we're introducing a bit more in probabilities this lesson, for the possible values of x are. So we know that for probabilities, we can go from 0 to 1, and it's important for us to recognize that sorry, I'm just doing something here. Okay. Very good. So it's important for us to recognize that we've got the variable and the probabilities. Now what's probability? Who can recall what probability is all about? Probability well, the first thing we know is that it has a range from 0 to 1. Anything outside that range doesn't make any sense. Okay? It doesn't make any sense whatsoever. Okay? Also, these probabilities, for example, could be a half. That can be expressed as 0.5 as a decimal. It can be expressed as 50%. Okay, so anything between 0 and 1 can be given a probability. And a probability is, we spend a lot of time in statistics because it helps us understand the likelihood of something happening. So in this particular case, what we've got is the probability of our variable being 0, and I want you to pay attention to two particular types, okay? The probability of x equaling something, dot dot dot, and the probability of an inequality, dot dot dot. And so at the moment we're looking at the equality, and this is one saying for this particular transmission system, the probability of there being 0 errors in the next 4 bits is 0.656. Now that's only 65%. So for this particular system, 0 errors, the chance of that is 65%. Okay, so it's not 100%, it's not absolute, okay, but it is a percentage. For 1 error in the next 4 errors transmitted, it goes down to 29%. 2 errors in the next 4 bits, 4%, so be careful of your decimals, just be careful of your decimals. And for this one here, it's 0.3%, 3 errors in the next 4, and for all of them, x equals 4 is less than, it's 0.01%, so it's a very small value. So we just need to be careful of that. Now this is when they're given this equal sign, what we can do is assign the probabilities in the form of a probability mass function. So the probability mass function, or PMF, okay, now you'll see 4 decimal places quite often in this course, so don't worry about that. In the absence of any kind of instruction, you would use 2, but generally speaking, don't use rounding on your probability at this point. If there's 4 bits, then that's your indicator, if you like. Okay. So probabilities apply. They're not is, they apply. They apply to discrete random variables. So remembering that a discrete random variable is a discrete step, on or off, alive, dead, all of those kinds of ideas, 1 or 0. Okay, what's the probability of that happening? So in this case here, we've got a PMF function and the probabilities associated. So I'm just going to put this one down here and say that the PMF function applies to this equation. Now this is very important, and so it's worthwhile me making a bit of fuss about, and I warned you when I did warn you that I would tell you when something is important and I want you to know it. Sometimes we have a functional form of a probability mass function. In other cases we simply have a table. So we might have a function that we apply, otherwise we'll have a table. The last PMF is shown this way. So there's our 0.65 for 0, for 1, and so on and so forth. And that looks very much like a function, doesn't it? That looks very much like a function. So what we'll do is we'll cross over probabilities and functions quite a bit during the time spent in the course. But today it's still introductory, so I don't want to get too... we're going to spend a few weeks on this, so I don't want to get too upset about that. Alright, so a little bit of math now. Basically the thing I want to draw your attention to for a discrete random variable is that for a PMF, it's the equal sign. I want you to pay attention to that, it's important. Okay, so we're going to learn to look for that in computer data printouts. So data printouts that are available to us, we're going to learn to look for that. And basically the other thing that we want to see is that I've kind of put that over here informally, okay, between 0 and 1. Alright, the values that we come out of the function are between 0 and 1, and the summing of the values is always 1. Now this comes about because if we take a distribution, now I'm mixing things up a little bit here, but the area under that curve is 1. Okay, 1 unit squared. So we say that area under that curve. Now we'll come back and do some more on that in the coming weeks, and we'll do some more on that when we do, well, R will do it actually in multivariable calculus later on in the session for spring. So at the moment I'm just getting you to point out that when the equation for probability has got this equate in it, okay, this equate, it's referring to a PMF. So we just need to be aware of that one, okay? And the summing notation also indicates that it's likely to be an integration. What's the extent of integration in the course? Probably U substitution integration. It doesn't get much harder than that. So it's not like we're going to bamboozle you with a whole bunch of really new techniques in this particular course. It will extend and build on what we already have, but it's not as complicated as you think. Alright, so in this particular example, we're asking for an error, our error variable. What's the probability, there's the what's the probability that it's between 2 and 3 inclusive? Okay, so what's the probability that it's between 2 and 3 inclusive? So if we use our table, now there's a couple of different ways to work this out. We can work this out by integrating functions. We can work this out by using other means, computational means, or we can just address a table. So we've got a table here, so we may as well do that. So between 2, there's our 2 and there's our 3, so it's the probability of the random variable falling in this space. This is called an interval when it's expressed with an inequality. And so what's the probability of our random variable falling within that variable? So it's fairly straightforward. I just go and pick 2 and 3, and I can just add them together. It's very straightforward. So P 2 x bounded by 2 lower and 3 upper, and so we'll get 0.0486, and we'll sum that to 0.0036, reading it straight off the table. There they're read and substituted in, and when I do the computation I'll get 0.05. So there's about a 5% chance of them falling within that range. Okay, so you can write approximately 5%. So this helps us to gauge and understand data when we're looking at probabilities. What's the likelihood of something happening? Okay, and it helps us to have a nature and an understanding. Now, I've already made the distinction over here about the other type of probability, and so we need to just explore that. So in this particular version, I want to draw your attention to this inequality. And this represents a cumulative distribution function, or a CDF. Okay, so when it's got this inequality, it's referring to a CDF. Now you need to be able to make the distinction because it has an application when we get to using the computer software. And I will go through some computer software in these lectures to help you to know how to do some of the work that's in front of you. So what we find here is that we've got some constraints on the values of these particular guys here, and it's just making that's not inclusive. So that's on the number line, that's like the open one. This one here is the coloured in one. I don't know if your training has allowed you to see that in the past, but hopefully it has. So that's an indicator of the interval. I probably should just break that. It's not relevant, but I just wanted to point that out. So they're not the same unless the PMF is equal to 0. So that's just a little qualifier there that we'll keep. We'll just keep that little bit of knowledge available for later on. And again, this implies that it's an integration, but I'll talk more about the mathematics of the statistics a bit later on. Alright, so what we're doing here is comparing the PMF and the CDF. Here's the PMF, okay, and so our PMF is using these equates. These are our exact values. Now how's the CDF? Well, it's cumulative, that's the clue. It's cumulative, so what we're doing is we're taking all of the values up to 1, all of the values up to 2, and what we do is we add them. So these values are still here in the CDF, it's just that they're being added. So we take this one, 0.65, and we add it to 0.29. There it is over there. So that's that 0.29. We add the 0.486. So this is, if you've ever done the histogram development at school, where you did the development of a histogram by hand, this is the same kind of idea. So in fact, it's exactly the same. All right. So, and then we've got a total of 1. No surprises there. So in effect, instead of taking, if I take this one, I'm in effect taking all of the probabilities beforehand. Okay. If I take this one, I'd be taking all of the probabilities beforehand. Okay. So if I've got a cumulative, I can look in here simply by subtracting those two. P4 and P2 would give me everything in the middle, but we'll come back to that. That was just an aside. Okay. So in terms of our previous problem, what's the probability that our random variable, is inside the interval 2 and 3 for errors, remember? Well, we did before 2 and 3, okay? We used the PMF. We said if the random variable is equal to 2, we can add that to the random variable when it's equal to 3, and that'll give us our PMF version of this computation. Okie dokie. What about if I do another calculation? What about if I take I still want to know what 2 and 3 is, which is here. So what about if I take that one and subtract that one. That'll leave me with everything in the middle here. So I can rewrite this. Now notice the form of the computation. The form of the computation would require us to have probability expressions with equates in them. This guy is going to use the inequates or the inequations. Okay, so they're two forms of the same kind of computation, but they're very, very different. Okay, so we'll get the same value that we got before. What was it, 522 or something like that? Was it double O or just single O? Let's go back up. Oh, 522, 5%. Okay, so in that regard they're still the same, but these are very, very different. Okay, so I just want to draw that to your attention, because you need to use a different technique for this one as opposed to this one. So we need to be mindful of what not only the probability computation is giving us in a context, and we'll get to that in coming weeks, but just in the mechanics of computation, we need to be a little bit careful of what we think we know. Okay? Alright, so the cumulative distribution function is a little bit different in shape. So the cumulative value of f of x, it's still got a peak of 1, but then each of the values are going along. Okay? So in the case of doing the maths version, what does that look like? Well, here's our, did you notice this is now CDF? Okay, have I done a good enough job of getting you to draw your eye to here and recognize that that is a CDF? Okay, and that's the one with this in it. Okay, it's got the inequation. So in order to solve the problem of this guy here, what we would do is subtract them. What did we do with the PMFs? We added them. PDFs, we've got PDF on the brain. With the PMF we added them. With these guys we are subtracting them. Okay, so provided we're consistent, then we just pull the value out and substitute and subtract, and just go ahead and do the computation, and you'll get 5%. Okay, and that approximates to 5%. Okay, so just pointing out for you the difference in the way the probabilities are presented. That's really all this, a very, very introductory idea of how the probabilities are presented. They can be presented as a PMF, they can be presented as a CDF, and you need to know the difference, and the fundamental difference is on the summary screen on the right hand side, which is one uses an equate and one uses an inequality. In particular, it uses the left to right inequality. So that's important, because we're not always going to get lovely left to right inequalities. Alright, so let's see if we can draw some more out. Alright, so we're going to talk a little bit more about the use. So, and when I talk about expected values basically represent, our expected value is the mean. It's a different name for a mean. Okay, so we can use these tables, the probability mass function as it's distributed in the table, and we can compute a probability for a problem. Now, I'm not going to have you come away from today all stressed about whether or not you can do these probability problems. You'll be able to. I'm just giving you a few simple examples, and I hold your hand and walk your way towards it, because that's important. And I'm not just going to hit you hard with a whole bunch of probability stuff. I'm just leaking out information at the moment as a general introduction, so that you can acclimatise and get used to this idea of probability. And then when the time's right, I'll ask you to do specific things, which is in examining you, I guess. But I'm never going to examine something that I haven't asked you to do or shown you how it works. So in this particular case, we understand what mean is when we add up and divide by, but how do we do it when we've got a PMF? Well, we just take a multiplication and we sum them. Because remember, that was the original equation, wasn't it? Now I'm getting a bit mathsy in doing that, but nevertheless, the general form of the equation held. So 2 times 2,000. I'm going to skip a few. 99, 100, and I'm just going to put 5 times 500, and all of that goes over the total number of students, which was 5,000, and so we've been able to get an average course allocation of 2.64. Okay, now that's a fraction. It can be written in another form. Just for your own information, we can split the fraction, okay, and add them up this way. Okay, and so on and so forth. But that's just fraction splitting, that's not really statistical sciences. So we've got 5 times 500. Same kind of computation, but I'm just pointing it out because sometimes for some reason it gets a little bit lost. Okay, I caught you up. Alright, so that was the probability mass function. If we look at the variable x in terms of its function, we can see that it's been proportioned already for us. So all we're doing here is multiplication and summing again. Okay, but this time the proportion is known. So for this example here, if we take that formal language, I don't want to bamboozle you with the whole thing. It's coming up actually, this, so I'm just kind of writing it in, being a bit cheeky. 1 to 5, because there's 5, okay, so I'm picking 5. And what are we going to do? We're going to take the x variable and multiply it by its function value, the PMF function, okay, and so we would get 1 times 0.48, 148 plus 2 times 0.4 plus ... plus 5 times 0.100, and so that fulfills that equation, and we get 2.664. So it's a kind of a new way using probabilities to determine our average. Did you put 2 and 2 together during this little talk? Did you say to yourself, hey, he's using probabilities to compute means? Did you get that far with your PMF and your CDF? I wonder. Did you get that? Okay. So that's where we've been a little bit cheeky in not spelling it out. So expectation or mean and variance can be used using these equations. Again, don't be concerned. Alright, the expected value, as I've already said, is our mean. Okay, so whenever we see expectation or expected value, we're talking about the mean. And of course there's our measure of variance. And so you might want to recall that the standard deviation is the square root of the var. That's what that says. So probabilities can be used to help us compute these measures, these parameters as well. Not parameters, but statistics as well. And that can be a very, very helpful thing. Okay, so a couple of computations. We'll go through 3 or 4 pages of computations. I got my tongue tied there for a minute, and we'll see that. So we're back on the PMF. Okay, so the expected value or mean is to sum the product of the variable by its function value, and so we'll have 0.0 times 0.656. So now I'm just multiplying 0 times this, 1 times this, summing them. Two times the probability, and keep going. 3 times, so computing means by using our probabilities and our functions. Did you know that you can do that? Well, there we go. And so we get an expectation or a mean of 0.4. We can work out the variance for x, and I think I've already given that equation. minus the variance total squared, and EX squared has its own equation. What would you expect? It's summing the variable squared times the function value. Okay, so we can do EX squared, so we just do 0 squared times 0.6561 plus, I'll skip a few, plus, and the last one was 4 squared. Okay, and we can use that information together. I've repeated the slide so I can just put our variance. So we're using probabilities to compute these statistics now. So I'll be very fair and careful in the way I unpack all of this for you. Okay, I'm not going to just drop it on you from a great height and leave you to wonder. I want you to engage with the subject, so part of that is me helping you do that. Okay? No, that's a different idea, Jeffrey. We're going to leave that for the moment, please. Okay, so we're just going to leave that for the moment, please. Xiao, I'm not so sure about that. I don't want to assign meetings between PDFs and CDFs at this point. Okay, we want to leave that for a few weeks, if you don't mind. Okay, but thank you for asking. They're not bad questions, but I don't want to have, I don't want to get engaged too deeply at this point. Remember, this is an introduction, and so I'm just trying to keep things fairly simple. Because I can already feel the tension going up. All right, I can already feel the tension going back all the way. Okay, so Ken Bin, what have you asked me for? This one? Did I get off too quickly? That's a really good answer. It is YouTube scrub back, but to be fair, I have asked you to engage with me on the chat, so I'm happy to do that. Okay, I would never tell a student to scrub back and look at it on their own time. I think that's demeaning, so I'm happy to take the request and respond in a very human way. Thank you. All right, so expectation and variance can be done. So let you guys do this. Okay, you can do this now. So there's your first one. You're going to compute a mean using probabilities. So off you go. You can compute this term. Okay, so you go off and do that for me now. Then we know the variance. How's it going? There's a couple of, sorry guys. There's a couple of kebabs there for you.
Like right now?
Yeah, 2 of them. Heat them up and a bit of rice, but that's not your tea. Sorry about that, folks. Life goes on when you're working from home. Okay, so just help yourself. All right, 101.1. Oh, I've given it away. Did you get that? So I've given that one away too. Did you all get that? Computing as you are a mean from probabilities. How wonderful. Okay. How did you go? Yep. You're squaring the, so the first term will be 8 squared times 0.03 plus. Up here it's just 8 times 0.03 plus. I know some of you will be annoyed when I do that. Does that answer your question? Okay, so you're able to compute. Does that make sense, Alec? Alright. I had a boss called Alec once. Okay, so. And what about the standard deviation? Okay, so the standard deviation for our variable x is going to be the square root of the variance to x, and that'll be the square root of 1.5, which is approximately, well, I should put 1.4999 in there, and that equals or approximates to 1.22 for a standard deviation, squished onto the page as I've done it. Alright, so anyway, enough about producing variance and mean using probabilities. Let's move on, shall we? Let's move on and do the next bit. Okay? Alright, so you didn't think you were going to be coming to uni and learning about doing probability today, did you? Not to this extent. Okay, so the binomial experiment satisfies trial. So this is just basically saying that if we've got a binomial distribution, and some of you will be twigging to this, and so in this particular case, an experiment can be classified as binomial on the proviso that it meets all of these. So by way of some examples that meet all of those, we can toss a fair coin 20 times, so that's 20 experiments. We can say that there's a successful event, okay, and we can call the probability 0.5 the probability of success, okay, and the probability of not success. So that would be, if I just write that down there, not success, which is really failure, I guess. But I want to just point this out. So the probability of success is P, and the probability of failure is 1 minus P, which is Q. Now we'll call this guy here the complement because it comes up a few times and we'll have to use it. Okay, so we'll be using that quite a few times. Okay. Alright, so in terms of binomial distributions, they need to be independent. They need to be identical. As identical as, yeah, replicable is another word I would use. Replicate, repeat. Each trial only has 2 possible outcomes, hence the reference to binomial. And then we express the success and failure. So we've got a bit of a task here to decide if these scenarios can be classified as being able to be used as a binomial experiment. So each of these represents a study-in case, if you like, of whether or not we can use the binomial experiment. So we need it to be repeatable, and we need it to have 2 states. So what are the 2 states for the first one? I know it's a bit gruesome and, you know, probably takes you back to year 7 when you did the rat thing, and it's all very sad, and there's great moral angst in the world at the moment about this. So, but for the moment we just accept that this is going on, and the study is about what are the states. So what are the states here? What are the states? Yes, Jeffrey, you called it. No, not a dice, a coin, because a dice doesn't have 2 states. A dice has 6 states. Okay, so we would have to reconfigure that to make it fit. We would have to reconfigure the question, the experiment. But the experimental design is a subject, actually, design of experiments. So some of you have pointed out, yes, you'd have to change the way that it was put together. Okay, but we'd have to change the dice as well, mate. We couldn't just use a subset. That wouldn't be right because the probabilities wouldn't be the same. Okay, so what is the probability that exactly 9 of them die? Well, the 2 states are alive. been dead. That's a bit gruesome, isn't it? So we qualify on that score. Is it repeatable? Yes, so it seems to be that we can model this as, are they independent? One rat dying doesn't affect another rat in the experiment, so we could say yes, it is a binomial experiment. Okay. A laboratory has 8 machines. They break down independently, so we're being told that when one breaks down it doesn't affect the other. 5% of the time is not really relevant to our problem. What's the probability that more than one machine breaks down at a particular time? So that's a good question. These are good questions in probability. The real question here for us though is just to type this. Can this be used as a binomial experiment? Well, what are the two states? What are the two states? So it's operating on, if you like, or it's failed. So the other state would be off. So it's got two states, so that's one criteria. We've been told that they're independent, so one machine breaking down doesn't affect the other. Okay, so in this case, working, not working is the same. So yes, we can use this as a candidate for a binomial experiment. All right, the next one. A narrow neck bottle contains 3 green and 3 black olives. Okay, now there they are in there. If we tip it on its side, and a couple of them spill out, does this qualify as a binomial experiment? Well, what's the problem? If that's a black one and that's a green one, who cares? Well, I do, because they're not the same when we start again. If we do a black one first, then we have one less. So now it's a different experiment with one less. The sample size changes. Good. So in this particular example, it is being affected by the previous test. Okay, so it fails independence. So it can't be independent. So we need to take that into account. Alright, so it fails independence. So it's just a little look at typing your experiments as we go. Now some of you will remember this. Again, don't fret, don't go bananas, I'll walk you through it. Okay, we say that x takes on a binomial distribution. So x such that it's a binomial distribution, x whereas it's a binomial distribution. Okay, with n and p parameters, so we've got probability and a number. Now the PMF for this particular one, what do we equate with a PMF? If it's a PMF, it should have, what should it have? An equal sign. So there it is. So the probability mass for a binomial distribution, now this is something that you would have picked up at high school, n choose x, or n choose x, or n choose r, and so these are factorials. It's fairly straightforward. So e.g. if I have a 3 factorial, I've got a 3 times, oops, just rushing a bit there, 3 times 2 times 1, 11 factorial, 11 times 10 times 8 times 7 times 6 by 5 by 4 by 3 by 2 by 1. So factorial algebra is interesting. So this is an example of some factorial algebra. Alright, so I'll be careful. I'm not going to just dump you in the middle of that. I'll help you when it comes time to do that. We are going to use that equation to help us with our probability. You haven't used it in this way. You haven't seen it in this form directly, I don't think. You've seen it used in other ways for expansions of higher powers. but for this particular case we're using it for a probability, so that might be new for you. Okay, so our probability distribution function for this example, okay, and so it's got that classic curve shape. Alright, so let's do an example using the distribution. The probability of successfully landing a plane using a flight simulator is given as 0.8. Okay, 9 randomly and independently chosen student pilots are asked to try to fly. Try to fly the plane using the simulator. So this is a good example of language and how we're going to manage statistical language. Okay, there's 3 versions of this, A, B and C. What is the probability that all the student pilots successfully land the plane using the simulator? So we've got some data, so we may as well line some data up. We're told the system has a probability of 0.8. We're told that the number is 9, and now we want x. What's x? Sea level. So what is the probability? Now this is the cryptic nature of this, isn't it? So I've been training your eyes to pick up certain things and your mind to think about certain things. It's just there inculcated in the sentence. What is the probability that all of the student pilots successfully land? How many are there? N is 9, so there are 9 in all. So for this case, and this case only, our random variable is 9. And so you're getting a little bit of an insight into the complexity of statistics. Okay, but we'll keep walking with it. Alright, so the way that we express it, we express that our variable is 9. Okay, and our equation is the classic equation that you've seen before and probably used on numerous occasions. Okay, and so we can expand that further to be 1 minus p n minus x p to the x n factorial over x factorial n minus x. Okay, so all we need now is make some substitutions. 9 factorial, 9 minus 9 factorial, so we'll get some 0 factorials here, which is 1, 0.8 to the power 9, 1 minus 0.8 to the power 9 minus 9, so just getting all the ducks lined up there, and so we've got 0.1342, which approximates to 13.42%. So the probability that all of the student pilots successfully land the plane is 13%. Really? Wow, that's not good. That's not good. So we're glad that they use a simulator, aren't we? Thank you for simulators, okay? And we're glad that they're able to do that. Alright? In terms of the next part, we're going to change the variable, and we're going to have to approach the variable idea. The calculation's fairly straightforward, but it's the variable idea. So what's the probability that at least 8 student pilots, so here's the language thing, at least 8 student pilots successfully land a plane? So we've got the same data, so we're not going to use that again. Okay, but how do we express the probability? Well, why don't we as a strategy phrase the question so that what is the probability that 8 students, okay, because the binomial calculation that we do is a PMF, it gives us an equal. Okay, oh, I don't know what happened there, I apologise for that. It gives us an equal, okay? So in that sense, there's no real point trying to compute something that's not equal. So our strategy then will be to compute an equal. Okay, sorry about the rolling of the screen there, that was just the magic of my wand. So let's compute it if it's exactly 8. Okay, there's 2 kebabs there for you as well. So we'll go through and do 9 factorial, 8 factorial, 9 minus 8 factorial. But at least is worrying me a bit because it's not equal to 8. So we have to come up with another strategy. Okay. And 9 minus 8. Sorry about the blur in the background. Which is 30%. Okay, so how do we address the question then? Oh, okay, so we know that we can do an interval and address this at least 8. So from a probability point of view, we would express this as at least 8. So it's equal to 8 or greater than 8. Now I've spent the time in bringing this to your attention because if I just gave you this part here and said suck on it until you can think about it, that's not an easy thing to do. So I'm pointing out to you that we've got this idea. Now the other problem some of you might have noticed, okay, the other thing, that's very good. The other thing that you might notice is that this inequality is around the wrong way. So we've got 2 problems. We've got to couch the question using the language. So the inequality is that way, so that matches this, great, at least 8. However, from a computational point of view, we've not learned how to do that. That's the one way round, okay? So what we need to do is recognise that we can do it 2 ways. Now it makes sense what I did before, doesn't it? We can compute it by summing the PMFs, because we have both of those. That will give us an answer, and we have done that previously. Not only have we summed the PDFs, but we have the individual values previously. Okay. The other thing that we can do, and I guess I'm drawing your attention to this, is that we can turn this inequality around. Instead of it being this way, we can turn this inequality this way. Okay, so how do we do that? How do we do that, and what goes in here? Well, the way that we turn the inequality around, now this is very important. We've got language. Okay, the way that we turn the inequality around is we take a complement. Aha. Okay, so a complement reverses the inequality. Okay, as soon as we write 1 minus, we can write the inequality. Now, in order for the inequality to match this, because we know this is matching the language, this is matching the language, it's the same language. In order for the at least matches this maths, so that language matches that maths, and we've just changed the inequality. So what is the maths that has to go in here? Okay, the complement means that we will be the next one down. Okay, so we would need to have a means of computing the CDF, which we've already been had it explained to us, for this one. Okay, so we would plot the we would need to calculate the CDF just to turn around the inequality. So it can get sticky if you're not if you haven't been paying attention. Now I'll take that off the other. I'll take this from another source, the 0.56. We're going to learn a couple of different 0.5 63792, and that is equal to whatever that sum was equal to, which is 0.4362, which approximates to 43.6%. There you go. Alright, so there's a few ideas in there. It doesn't get any, I know that sounds mean, it doesn't get any worse than that. So we've got to match the language to the maths. If the inequality needs to be turned around, we take an equate. Okay, so just watch that space and we'll do some more on that. Alright, let's do another practice for this. What is the probability that at most two student pilots fail to successfully land the plane? Okay, so to help you with that, what is the probability that most two student pilots fail to successfully land the plane? We need to convert that into a matching PMF or a matching CDF. So that's what's happening there when I'm moving my pen across, it's jumping. Okay, so in this case, two or more 2, 1, 0 fail, that's the question. Okay, as it's couched and phrased in the question, so that is the same as what? 7 or more succeeding. Okay, so that just tells us that we've got a little bit of work to do in this process. So 7 or more succeeding will be this guy, and so we can do that two ways. We can sum them together, or we can take a complement from a CDF. So we would turn that around. What's the number that goes in there? Okay, so we can compute the CDF and take the complement. In this case that would be 6, which is 1 less than 7. So this is 1 minus 0.261, and which is 0.7382. Yeah, that's right. Which equates to approximately 73.8%. Alright, so I've introduced the concepts of probability at the level and complexity that I want to today. I don't necessarily want to get any harder than that. Certainly I haven't introduced complicated mathematics to this as well, and obviously you could see that to compute your PMFs and CDFs by hand might be a bit tricky. Okay, so we need to think about that as we go forward. Okay, no, because less than or equal to would be less than or equal to for the fail case. Remember, they're success items. They're not fail items, they're success items. So that's all it is. Okay. Alright, so here's a in-your-face version of the binomial theorem, computing our means, aren't they? Expectation. How simple is that? How simple is that? Okay, so to count the means for this particular example, 10 times 0.7 is 7. To do the variance, wow, this is a simplified derivation. I don't prove this for you, and I don't ask you to prove it, but it could be done that way. 0.7, oops, 1 minus 0.7, I might just squish that up a bit. And so we get a variance of 2.1. So they'll all agree, all those different forms of doing the equations. I've had an interesting question there. Fail items. Well, that's what we did here. That's what we did here. No, because the probabilities are about success items. The probabilities are about the successes. Okay, So we take, that's just a blank slide. I didn't need to put that one in, but I've left it there for you. All right, so the last couple of things I want to get to today are one more example. And so basically your training is going to lead you to notice these data outputs. So this is again a big hint because it's about the kind of skills you'll need for your exams in stats. Okay, so I'll put a bit of a marker there. And what's your training doing? It's saying that we've got a random variable. What's the probability if the random variable is 5? It's a binomial distribution. We're given the number and the probability, and here it appears as a Minitab distribution. There's the information straight out of Minitab. Okay, this one says find px equals 5. So px equals 5. Well, wait a minute, we just said that we could make some really dangerous calculations, and what you're doing now is you're saying, what? Really? Read that off. Is that all I've got to do? Okay. This one here says read x greater than 5. So how am I going to read x greater than 5? How am I going to write that? Maths. I'm going to take the complement. Okay. So the probability will be the success case for 4. And so we can read this off here. And 1 minus 0.6. And we've turned the inequation around, and so we can read it off the distribution function. Some of you might be starting to realise the reason that we use the complement in turning the equation around is because we get the PDF from Minitab and we only get the CDF for the success case that way. Now when I explain how these computations are done using integration in a couple of weeks' time, not that you'll be required to do that, but that you'll at least observe them, this now makes perfect sense, the limitation of what the computer systems can do. And it doesn't matter what computer system you use, they have the same types of limitation. So we've been able to work out the probability for at least 5 and equal to 5. Alright, there's an example now of probability for intruders A and B. I'm quickly just going to put those together without speaking much to it. I'll let you mull over those in time. That's the other way. Okay, so there's the two types. We get the CDF off Minitab or wherever, or we compute it by hand. So only 17% of the time can they detect intruders. And what about fewer than 4? So we can do 3 or less, because it says be careful of the language. Fewer than, doesn't say at least or at most, it says less than, fewer than. Okay, and we can read that one straight off. Alright, so again 17%. So that's pretty much it for today. I am just going to show you one thing. Okay. And And basically what I'm going to do there is enable something from an old announcement. There it is. So I'm just, if people wouldn't mind going on to UTS Online at the moment. And if you scroll down, I'll bring it up to the top. The language of statistics. And because we have to match the language with the mathematics, now we're dealing with PMFs and CDFs and probability. And so the way that we do that, so if you wouldn't mind just going to MM2 your announcements. Okay, I've put an old announcement right at the top there, just after Taleb's announcement. And so basically it's an announcement that looks like this. Okay, and what it's doing is it's showing you the use of inequality and its language equivalent. Now the language equivalent is something that you guys are going to have to get your heads around. That's where the bugbear is for the subject. It's in the language. Okay, so when we translate that, no, it's too long. Actually, the computation for I've been asked to do the calculation real quick and I'm assuming that means the integration one. The density functions and the distribution functions need numeric techniques, and that's the crux of the lesson that we cover when we do that in a couple of weeks' time. And what it basically says that it's very advanced techniques because of the equation, and it's better that I leave it until that time, I think. If you could just be patient, and we'll get to that. Okay. Alright, I'll explain where those numbers come from in coming weeks, because we're going to start fishing out values from a particular location, and that's tied up with the explanation of the integration function. So you're just going to have to be patient with that. They're given at the moment, but as we examine the PDFs and the CDFs more, then that'll become apparent where that's coming from, and you'll be doing that yourself. You'll be fishing those values out yourself. So rather than make you do horrendous calculations, I've got a tool that helps you do that. Okay. All right. So this is the main thing for today. You've learned probabilities, how to get your means and variances using probabilities, and then we go for the language. Okay. So the language is a big part of stats. Everybody wants everything straight away. So that's all I'm going to do today. That's all I'm answering. I'm not answering that question. Okay, so you can be patient and wait, and we will get to the use of that. But it's good that you're keen, so I'm not being mean to you. I'm just asking you to wait a little bit longer. Focus on what we looked at today. Have a good read of it. Think about your probabilities through a different lens now, a very doable lens, and a way of computing these statistics using probabilities. Okay, not at the moment, you don't know. I'll show you where that comes from in due course. Okay guys, thank you very much for coming along today. I do appreciate it. I'm going to wind it up there, so I'm going to say thank you very much. Okay, well done. And I will see you next week. Thank you for coming along. So Mark has asked me a question. I'm happy for you to switch off now if you want to go, that's fine. Sorry, I'm just going to do... Thank you guys. Thank you for all of those well wishes. Got a question about the tutorial. No, the subject timetable, there's lots of tutorials. There's lots of tutorials. That was just one message that he put out on the announcements. So I think there's more than one tutor for this subject. I'm not running the subject, so really they're the kinds of questions you need to ask Ara. But yeah, it's different. There's a host of them. It's a very big. There's lots of you. So there's lots of tutes and there's lots of labs. So just stick to your timetable, and you can be reassured that that will be fine. That specific question wasn't about a tute so much as it was about a lab, but I hope I've addressed the lab idea. Okay, just stick to your timetable. Your timetable is the right place to be. Okay, I hope that's helped. Again, ask your tutor, ask Ara. I don't want to get into that. Okay, thanks, mate. Thank you. You have a good afternoon too. Thank you. All right, see you guys. Well done. I'll see you next time. Bye now.